In this video, I want to do a quick recap of the things that we've learned about torsion and then solve one more kind of involved problem. Let's start by reviewing what our sign convention is for torsion. When we are solving torsion problems, we are typically looking for either angle of twist or shear stress. In both cases, we need to find the internal torque. So it is very helpful to have a sign convention for internal torque, and the sign convention that we are going to use involves the right hand rule. So if you take your segment of your shaft that has a constant internal torque and you put your right thumb pointing out and away from either ends, we're going to call that a positive torque. And you could think of it as if you point your thumb in the direction of either of these double-headed arrows, you will end up with a rotational sense that looks like that on that end and like that on the other. They should be equal and opposite. Internal forces, internal torques always come as equal and opposite pairs. So there is our sign convention. With that, we can then use our angle of twist equation, which says the angle of twist in radians is equal to the summation of the internal torque times the length that it acts over divided by the polar moment of inertia of that segment times the shear modulus of that segment. And when we're doing this, the sign of the torque matters. T is always going to be the internal torque in each segment of our shaft. So we are going to need several little free body diagrams. Those little free body diagrams are where we cut the shaft open to identify internal torque. If I had several wheels, and at each wheel we have different torques. The torque that's applied at A, torque that's applied at B might be in a different direction. Maybe there's the torque at C, and maybe here is the torque at D. If I want to actually find the angle of twist here, I do not directly use TA, B, C, or D. Instead, I want to cut open in between A and B to find the internal torque in segment AB. I want to do a separate free body diagram cut between B and C to find the internal torque in between B and C. And finally, do a cut in between C and D and find the torque in between C and D. Those are the three torques you would use in your equation over here to find the total angle of twist of a shaft like this. So don't directly apply your given torques. Take your cuts, do your free body diagram, find your internal torques. Once we do find internal torques, we can use them in this equation to find angle of twist. We can also use them to find stress. Remember the equation for stress? The equation for stress in a torsion bar, the stress is a shear stress, and if I want to find the stress at a location, I would need to plug in the internal torque at that cut on the cross section times the radial location that I want to find the stress divided by the polar moment of inertia. The picture that I like to use for that is cut open the shaft and you found the internal torque. Say here's the torque at point E. If I want to find the shear stress at point E, I need to find the torque cut through point E. And let's say point E is not on the outer radius, but it's right there. Well, we could figure out what to plug in for rho by simply measuring how far out from the middle do you have to go, where R is the total radius. If you wanted to find the stress at the outer edge, you would plug in R for rho. If you want it somewhere else, you plug in the radial location rho. And if you ever wanted to find the maximum shear stress, tau max is equal to the shear stress evaluated at rho equals R. So plug in your outer radius, where R is your outer radius. And our book tends to call it C. I don't like to think of it as two separate equations. It's one governing shear stress equation. If you want the shear stress anywhere, you plug in the radial coordinate. And if you want the biggest shear stress, you plug in the biggest radial coordinate, which would be R. About that direction of shear stress, this is something that causes some students difficulty. Well, I like to start with zooming in on the cut open face. So if this is my cut open face here and I've got an internal torque T right there, I like to draw these little arrows where I just go around the outer perimeter of the circle in the direction that that torque is acting. And then if I want to draw the direction of the shear stress on a point over here, so I like to draw a little cube that has a similar perspective to the other picture. So I'm going to start, maybe make it look kind of like that. So the idea being that these lines are supposed to be kind of parallel to that. And this face right over here coincides with this face that you kind of be looking at from this direction. So if I'm drawing the stress at this point right here, look which way the purple arrow is going right there. It's going straight down. So on the face that matches it, draw your arrow going straight down. And if you can get that arrow on there, you are 90% of the way there. Now, I don't make a big deal about drawing the shear stresses on the sides of this cube that I can't see. There will be a shear stress acting on the back face that is equal and opposite. And if I do have those pairs, you'll see that this would start rotating that way. So to counteract that, what we end up with shear stress is a second pair of shear stresses that will be on the top and bottom face that create exactly an equal and opposite rotation to the two original arrows that we had on there. I don't think you need to draw these ones on the hidden faces. I think it just makes your drawing look kind of cluttered. So if you can get this one, this on the front face comes from the actual downward arrow on that circle. And then this comes from simply wanting to match them up tail to tail or head to head. Let's pick another point. Let's say I wanted to find the direction of the shear stress right down here at the bottom. Well, I'm going to do the same thing. I'm going to draw a little cube, similar orientation to the one I already drew, and right down there, the purple arrow you can see is going to the left, so I want my purple arrow to go to the left. And again, this time, instead of putting my other arrows on the top face, I want to put the arrow on the face so that I get those heads pointing right toward each other. Like here, I wanted to have those heads pointing perfectly away from each other, so I did not draw anything over here. I kept them tail to tail, and in this case, it's head to head. And just for fun, let's do one more location. Let's do this edge over here. Draw one more of these cubes. Over here, the purple arrow is going up. You see that? It's going up right there. So I draw it up right here. And again, you want to make your arrow on the other face that you can see so that they are head to head. That's kind of a quick review of how we draw these little differential volume elements to indicate the direction of shear stress. Let's do one big fun example. Here is a torsion example. It's not too complicated in terms of the torque. This is simply a shaft that has a torque applied to it. The torque is actually applied in the positive direction because those double-headed arrows are coming out. And here are the governing equations we're going to use. I already gave them to you. Our shear stress equation and our angle of twist equation. We are told the material is steel with this shear modulus in PSI units, and we're given an allowable shear stress of 12 KSI. First, I'm going to solve part A. It wants us to find the maximum torque, and at that maximum torque, what is the angle of twist of this 8-foot shaft? So let's do that part of the problem first, then we'll come back and look at B and C. We have an allowable shear stress of 12 KSI. I want to set that equal to tau max and see what I can solve for. Well, let's pull up our stress equation. It says tau max is going to be T rho, I'll call it rho max over J. Our max stress always occurs where we are at the maximum radial location. So given that this shaft has a 6-inch diameter, rho max will be half of that, 3 inches. So let's fill this in. I want to solve for T. So rearranging, I will get that my T that I'm going to solve for, it'll end up being my maximum value of T is going to be equal to tau max times J over rho max. There's my equation rearranged. I know tau max is 12 KSI. I know rho max is 3 inches. I need J for this problem. So J is going to be pi over 2 times the radius to the 4th, but this is hollow. So we're going to do pi over 2 times the outer radius to the 4th minus pi over 2 times the inner radius to the 4th. Looks like 2 inches. So J comes out to be 102.1 inches to the 4th power. We plug that in, and we get T max is 12. We'll write it as kips per square inch. Remember, a kip is 1,000 pounds. J is 102.1 inches to the 4th. And rho max is 3 inches. Let's check how our units are going to cancel out. I've got inches to the 4th on the top, and I've got inches squared, inches cubed basically on the bottom. So I'll be left with units of kips times inches. Those are okay units for torque. It's a force times a length. And doing this, I get 408 kip inches for my maximum torque for part A. When you apply that much torque, you will end up with a maximum shear stress of exactly 12 KSI. Problem also wants us to find the angle of twist. Our equation for that is phi is torque length over polar moment of inertia times g. I now know my torque is 408 kip inches. The length was 8 feet. Let's convert that to inches. There are 12 inches in 1 foot, so that conversion factor will get me into inches. And then in the denominator, I will have my J, 102.1 inches to the 4th, and G. G was 29 times 10 to the 6th PSI. I don't really want PSI, so I can convert that to 10 to the 3rd kips per square inch. The reason I want kips is that I also have kips up here on the top. So 10 to the 6th psi is also 10 to the 3rd ksi. Let's cancel. So our feet cancel, kips cancel, and on the top of the fraction, I've got inches squared. On the bottom, I've got inches fourth divided by inches squared, which is also inches squared. So all of the inches will cancel as well. And I'll be left with dimensionless, which is good for an angle. And we interpret that as radians. We end up with 0.0132, and that will be radians. We've done part A. Let's look at part B. What does part B ask us to do? It says we're now going to replace this with a solid shaft that has the same weight. And we again want to find T max and phi. So what does it mean to keep the weight the same? It means we're using the same amount of material, but instead of a hollow shaft, we're going to make it solid. Part B, I'm going to have to solve for the radius that would be the same exact weight as a hollow shaft that had an inner radius was 2 inches and the outer radius was 3 inches. So I want to solve for R so that they have the same weight. Okay, well, for them to have the same weight, they're made out of the same material, which means the materials have the same density. We need to use the same volume. We're assuming we're still 8 feet long. So the only thing that you can really change is the area. In order for it to have the same weight, given they have the same length, the same material, same density, they need to have the same cross-sectional area. And you see that if they have the same amount of cross-sectional area, you multiply that by length to get volume, you multiply volume by density, then you finally get weight. So as long as their areas are the same, their weights will be the same. The area of the hollow one is pi times the outer radius squared minus the inner radius squared. We want that to be equal to the area of the solid one. It would be just pi r squared. We're going to solve for r because we know that the outer radius originally was 3 inches and the inner radius was 2 inches. The r for the solid that has the same weight is 2.236 inches. All right, now we use the same equations that we just did. Our shear stress is still T rho over J. So rearranging that, our max torque is going to be our max shear stress times J over our max radius. Well, that's going to be 12 kips per square inch for our max shear stress. J is, maybe we should calculate J separately. J now is pi over 2 times my new radius, 2.236 inches to the 4th. That happens to be 39.3 inches to the 4th. So J is quite a bit smaller in this case because it's solid instead of hollow. So plug that in, 39.3 inches to the 4th. And then our max radius is also smaller, 2.236 inches. Calculating all of that, we get T max is 211 kip inches. So interesting, use the same amount of material, but instead of making it a nice big hollow shaft, you make it a small solid shaft, and you'll notice how the amount of torque we can carry is roughly half what we could carry with the hollow one. Let's also look what happens to phi. Our angle of twist is TL over JG. Our new torque is 211 kip inches. Our length is still 8 feet, which we still need to convert into inches. J is smaller now, 39.3 inches to the 4th, but G is the same. That's our 29 times 10 to the 3rd kips per square inch. Those units will cancel out just like they did before. We end up with 0.0178 radians. I don't know if you find that interesting or not. We're applying less torque and getting more twist than we did with our hollow shaft. So the hollow shaft can handle more torque without failing, and it will also twist less than the same exact material in a solid shaft. Let's do part C. Now we want to keep the weight the same, but have a very big outer diameter. See what our max torque and our angle of twist look like. In order to keep the weight the same, we need to have the same area. So you can use either of the ways that we calculated area before, but this time we're going to have something that is probably very thin, but we know that it has an outer diameter of 8 inches, so the outer radius would be 4 inches. If we're doing the same area, let's go back to our original shape. We had pi times 3 inches squared minus pi times 2 inches squared, or factor the pi out. That has to be exactly equal to the green one, which is going to be pi times 4 inches squared minus pi times the new inner radius that we want to have squared. So the pi's actually cancel. Solving, we get that the new inner radius has to be 3.317 inches. Let's go ahead and calculate J because I know I'm going to need it. J for this new one is going to be pi over 2 radius to the fourth is 4 inches, which gets radius to the fourth. And then we want to subtract from it, if you're factoring out the pi over 2, 3.317 inches to the fourth. And that number comes out to be 212 inches to the fourth. Let's calculate our max torque now. T max, remember our equation was tau equals T rho over J. So T max is going to be our max shear stress times J over our max radius. Max shear stress is still 12 kips per square inch. Our J is now 212 inches to the fourth. Now our max radius is 4 inches. It's bigger than either of the other two cases. And solving, would you be surprised if I tell you we get the biggest torque of all? We do. We get 636 kip inches for our maximum torque. And what about angle of twist? Well, it's still TL over JG. Our torque this time is the biggest, 636 kip inches. Our length is still 8 feet that we still need to convert to inches. I might have saved myself a little time by actually calculating that number once, but it's okay. J is now 212 inches to the fourth, and G is still 29 times 10 to the third kips per square inch. So running all those numbers, we get 0.00993 radians. So it's the biggest torque of all, but it is the smallest amount of twist. So if you were designing a torsion shaft and your primary considerations were carrying as much torque as possible or reducing the amount of twist that happens when you apply that torque to it, you want to go with the biggest outer diameter you can, keeping the weight constant. That may not be your only design consideration. In theory, you could make the shaft get really, really big with a very tiny wall thickness. That might not be practical for a couple of reasons. One is clearance requirements for where you're putting this shaft. You might have a maximum size you can go up to. The other thing you can run into is if this wall thickness gets too small, then even though in theory you could twist it really with a giant amount of torque and have very little twist, you can actually start to have crimping of the section. So if you tried to actually apply a very large torque to a very thin shaft, it might actually crush. So there are practical considerations, but everything else being equal, you will get more load carrying capacity with a hollow shaft than with a solid shaft of the same weight.